Namaste and welcome everybody to the Python programming bootcamp. This is session 3 and thank you all for attending the previous sessions. I'll share my screen. We are being recorded. Okay, in the previous session we discussed a number of things. These include some simple programs that were covering Armstrong, Fibonacci, and swapping numbers and transpose. And then we saw a very simple program about summing a matrix. And then we discussed about a cashier program where we were trying to give a change. Unfortunately, I have not received any feedback about exercise 1 from anybody actually. So it seems that either people are spending time to do them or they're just spending time to see these videos. Either ways, I mean, if you have done something, please do share. Please give me some feedback about it, how easy or difficult it is, something like that, a personal message or a message to everybody so that we know how we are going, okay? The purpose of this bootcamp is to ensure that you learn. But the thing is, quite frankly, you will not be able to program by just looking at these bootcamp videos. Roughly for every 2-hour video, you must spend 5 to 7 hours of your time. So that's why it's a bootcamp where for 2 weeks you should not do anything else. But I know people are all busy doing a number of courses, a number of projects. So the way you can do it later is because these videos are online, and you see the videos again, and then you see each session as a week, you know. So see the 2-hour video for each session and spend the time on the exercises thinking that you do the exercise for the entire week or 2, something like that. So you can think of this as a 1 semester course even. And in that way, basically, you get more and more time to practice. Right. So, okay. So this week, what do we have? Session. Right. So we have session 3 here, and we are going to go over some simple programs again. And the Armstrong number that we covered last time, we'll go over it again because I did rush a bit yesterday, I think, and quite frankly, I was a bit dizzy yesterday. I was having some allergies, and with these allergies, it becomes difficult for me to explain things. So today, I'm feeling much better. So now we'll go over the Armstrong number, okay? Again. So what is the Armstrong number? It's also known as a perfect number or a narcissistic number. It's a number which can be compared to some operations, right? And what are those operations? So for example, the lowest Armstrong integer is 153. So how do we know that is an Armstrong number? So you take that number, let's say 153 is the number, and then you kind of check how many digits are there. So that's 1, 2, 3. So 3 digits, right? Right. So then you take the first of the 3 digits, and then you place it. So you put it to the power of the number of digits. So 3 is the number of digits.
The tiger came to a tea party.
3 is number of digits.
Read about the watch a tiger.
So if the number was 1124, number of digits.
Yeah, the letters. It says universal.
4.
Wow, it's the start of a movie. Wow, look at that.
4, and then this the calculation would be a little bit different for that. But here, let's continue with 153.
Sounds
Then you take the
delicious. What do
next
you
one,
eat?
and then you
Delicious.
raise that to the power of number of
Yeah,
digits.
Tiger coming
Then
to tea
plus
party.
the last one.
It says the
is 3 to
tiger
the power
who
of
came
number of
to tea.
Okay. So that's
Based on the book by
basically
Judith Kerr.
Armstrong number.
I love these these
Let
book
me-
adaptations.
let
Yeah,
me mute
book
this.
to cartoon. Look how beautiful this is. Wow.
Okay. Everybody is muted. So please mute yourselves. Yep. So okay. So how do we do this? Now we need to know. We know that for all the numbers, what are you going to do? Is you're going to do this operation. Okay. So if it was this number, let's say 1124, then it would be what? Can you please put it in the chat? What would that be expressed as? That will be great if you can try and put it in the chat. So while I am also writing, don't look at mine, please. Just write yours in the chat. Okay, let's see what you have written in the chat. Okay. Can you hear me now? Can people hear me properly? Okay, great. Okay, great. Thanks so much. So you guys have solved the puzzle. Nothing. And then now you say you calculate what that number is. Now you calculate what that number is. Right. So where is this? Any idea? Anybody done it? You can quickly use the Google calculator, perhaps. So that's some of them are quite easy, right? So you have 1 to the power of 4 is just 1 plus 1 to the power of 4 is 1 plus 2 to the power of 4. So 2 to the power 2 is 4 times 8 to the power, is it 32? Yes, no. What is 2 to the power of 4? 2 times 2 times 2 times 2. Anybody? Okay, 2 to the power of 4, 16, not 32. Okay, great. Thanks. So 16, and then plus, what is 4 to the power of 4? 4 times 4 times 4 times 2, 5, 6. Thanks, Anj. So what is the total here? 256 plus 16 plus 1 plus 1. So that's definitely 18 plus 256. And that's 7274, right? Thanks, Howzu. Sorry, how you? Thanks. So right. So the question is 1124 same as the number 274? Yes or no? So is my question to you, is 1124 an Armstrong number? Anyone? No. Thanks, Gordon. Gordon says no. Anybody else? So 1124 is not an Armstrong number, according to Gordon, and seems most people agree. So nobody is contesting him on this. Right. So let's move on. So how do we do this? So we can see that there's a series of operations here, and the series of operations basically mean, first thing is that you need to know how many digits are in the number, right? So the number of digits basically is taken by this simple length of a string. So the number, which is an integer, it's just converted into a string, and we just try to find what length it is of the string, right? So in the case of 153, the length would be 3, right? And then it's saying that you place that number in as temporary, and then you do a modulus 10. Why this is done? Temporary modulus 10. This is done because you take so what would be 153 modulus 10? Let's do this. What is 153 modulus 10? So temp is now temp is 153, and then what is temp modulus 10? Anybody? Anybody wants to try 153 modulus 10? So 3. Okay, great. So what is this 3? We can see this 3 is coming somewhere from 153. Okay, that's the last digit actually, right? So we can print that, and then we will do that whatever the temporary is, which is 153, divide by temp is equal to temporary. So what will be here? What will be the temp now? 153 temporary. Anybody? So 15. Okay, great. So 15 is temporary. And then we take we still use the same order order value. We don't need to do this order again because that's done once. That's fine. I just try to copy what's in the loop. So we already know what the order is. So then we take that 15 and then we do a 15 modulus. So because our temp is 15, 15 modulus 10. What is 15 modulus 10? Anybody? 15 modulus 10 is 5. So 5 looks familiar in 153. Okay, it's the middle number. Okay. And then 5 divided by 10. So the temporary is changed. Okay. Let's just see what it runs as. So we right. So just note that the 2 are these things and the 3 is the temporary. Okay. So Python, sorry. I'll just go into my folder, simple programs, and then in there, sorry, Python, strong. Right. So in the beginning, we did get this 3,327. Why? So it was the order was 3, and the digit that we got was temporary modulus 10, 3. Then digit to the power of order is 27. Okay. So that's what we saw. And then the temporary value was updated to 15, which we saw ourselves. And then we did a digit. Then we did a modulus 10, which we get 5. So now we have power is 3, or the order, and then the digit that we get is 5, and then 5 to the power 3 is 125. Okay. So basically that is there. And then basically what is in our temporary is, because 10 divided by 10 is essentially 1. So that's what we get in the temporary. And then we do another time, and that time basically we get 311, and then we get a 0 at the end. The temporary becomes 0. So basically you can do this operation till your temporary becomes 0, and that's why the temporary greater than 0 is the condition in the while loop. Okay. And then basically we're trying to see this, the same operation is there, which we just saw, but actually because there's a sum plus and we introduce a sum there and starts from 0 and whatever digit to the order, this basically computation is actually done here. So that's what it is, you know. So if the number of digits was 1 million, then it will be done 7 times, the sum, the operation will be done. So you can see, so, and then the temporary is updated and the whole operation, you just keep on adding to the temporary. And what then you do, whatever is the sum, you compare that with the original number. All right. So in the case of 153, it gives 153. But in the case of others, it will not give this won't be the same. And that what we can see is here. So in the range from 1 to 2000, we get only 1, 2, 3, 4, 5 of these numbers. By the way, I did a quick Google search of the number 153, and in Wikipedia there's some it's an interesting number, and our case is narcissistic, and but it has some reference to the Bible about something. Okay, so that's something to read about. So different cultures for a long time have and religious bodies for thousands of years they developed, and some of the numbers are seen auspicious in some religions. For example, in Hinduism and Buddhism, number 108 is auspicious. So there's a lot of things we Hindus and Buddhists do 108 times because it's an auspicious number. For example, the meditation beads, there's 108 beads in there, and then we use it for meditation. So ancient societies and civilizations were quite interested in these number systems, and they mark some numbers as auspicious and some as sinister as well. So for example, the number 666 represents the devil in Abrahamic religions, which is also interesting. So okay, here just to note that in this program there was no functions. Okay, so the program just started executing from the top and it went all the way to the bottom. Whereas the programs, when you have a function, whatever is on the top will not be executed, and whatever is only on the bottom will be executed, which we'll see next. For example, if we want to compute the greatest common factor, highest common factor, or the greatest common divisor. I recall we used to do this towards our end of primary school or the beginning of high school, something like that. So this is quite interesting. So the GCD, so it's the same thing. It's either highest common factor or greatest common divisor. Okay. So to compute that, let's say for example, the GCD or HCF of number 12 and 14 is 2. Okay. And what is the GCD of number of 24 and 6? Anybody? GCD of 24 and 6? Anybody? Nobody wants to try. You can be wrong. Somebody is saying 6. Okay. So Tiani is saying 6. Is it correct or not correct? We'll find out how we are going to use our function here. Okay. So let's run this. so because it's a function, that's what I was getting at. This whole code is compiled, or the Python, I mean, is generally the interpreter. Python is an interpreted language. It's not a compiled language, meaning that when you compare it with something like C and C++, in there you compile and then you have an executable file created. But in Python, you just run it. So Python and PHP, these are all interpreted languages. So you don't create a software file for it. There are the advantages and disadvantages of that, which is you can read about. Okay. Okay, so what happens here? Now, let's look at the. So the first thing is, what we are doing is we are trying to find the GCD of 54 and 24. Okay. So it loops and it does all these things, and it says that the HCF is 6, right? And let me go into a simpler case, the 24 and 6. 24 and 6, which I just asked. So it is saying, so Tiani was correct. The HCF is 6, right? So how is that computed? So you can see that we are using a function, and in that function we have a for loop. Basically, first thing is that you try to mark what is the smaller number out of that. So in the case of 6 and 24, our smaller would be 24. 6 is the smaller, right? So 6 is smaller. So it depends which order you give, right? So what is your X and Y? And in our case, the number 1 was 24 and number 2 was 6. So it was it's the other way, 24 and 6. So basically 24 and 6, and 6 is smaller. Otherwise, if it was the other way around, in the other order, then 6 would be smaller and this would be executed. But till the smaller number, you start from 1 and you go all the way to the smaller number. So 1, 2, 3, 4, 5, 6. Okay. That's why it's 6 plus 1. The reason it's 6 plus 1, because we know that in 4 loops, the last number is not included. Okay. So that's why it's 6 plus 1. So you just print, we are just printing this just for our own understanding, right? And so what is doing here? So it's printing the I, and so for the I and the smaller, right? And then it is finding, it's doing a modulus of the number that you had, the X, which is 24, modulus I. So your I is at the moment 1, right? Your I is 1. And what is 24 modulus I? So 24 modulus 1, if it is checking, if it is 0, and the Y, which is your 6 modulus 1 is 0, then your I is your HCF. And in here, basically, this becomes true because both of these are true. So this is true. That's why we see this being printed. So in the case of, so your HCF is then 2, then your HCF is then 3, okay? Because it's 2. But for 4, 5, and 6, the HCF is, one of these statements is not true, so that is not printed. So then basically it just returns the HCF. So your HCF keeps on so your HCF is here, and that keeps on being updated as it when it's true, and then basically that is returned. Okay, so that's how the algorithm works. So another thing is there's another way, a more shortcut way of implementing it with this Euclidean algorithm, and you can try to print things out and try to understand how this works. And we will move into the next one now, which is a guess game. Okay, so this is very simple. So it's just a guess game, enter integer 1 to 99, between 1 to 99. Okay, I enter number 45, and I am supposed to guess a number which is between 1 to 99. Okay, so it's saying guess is high, and that means I should now put a number which is lower than 45, let's say 34. It is saying guess is high, then let's say 23, too low. So now I know that the number should be between 23 and 34. Okay, so try to run this and also play, please. Maybe you can guess faster than me. So the guess is high, 23. So it's saying high, and the lowest number that I placed was 23, and then I said 30. It's saying high, so it should be between them. Let's say 25. It's low, 26, low, 27. Yes, so I guessed the number. So how many times, how many iterations I took? Probably that could be given as the number of points, how many times I took to guess it. So that's the guess game, and how it is implemented. It is just a very simple random number generator. You use a simple game and you use a random number generator between 1 to 99, and then you give that number to the function, right? And this is the function, and basically the function asks the user to give the number from 1 to 99, and then it has these three conditions, and that's what you saw as that it's between high and low. So it's just see how creative this game is, how creative is the solution. Very simple solution, very simple game, but it demonstrates the use of a repetition function and a random number generation. Okay, so this could be when a friend of you who has no programming knowledge wants to learn programming from you. This would be a good game to, good example to show them, right? And then now the final one of these simple programs, we have simple program that checks if the number is prime, and you need to list all these numbers that are prime. Okay, so we will go and run this. Is prime. So between 900 and 1000, between those two intervals, basically the program checks if the number is prime. And as the function, the definition of the prime number is that the number is not divisible, basically. Only it is divisible by itself, right? So how is that implemented? Basically, the lower and upper range is given using the for loop, and if you want with the for loop to have an upper and the lower range, and then you are incrementing between the upper and lower range, that's how you do it. And you just see if the number is greater than 1, then you have you use a for loop, and then you check if that number is divisible by I, then you break, else you print the number. So that means if the number is divided, basically you know that can be divided So if the number is, let's say that we do a simpler example. So we start from 0, 1 to 10. Okay. So so the prime numbers between 1 and 10 are 2, 3, 5, and 7. Okay. So essentially, just the modulus operation is used to determine that. So I hope this makes sense to you. A number of these examples, I'm kind of rushing a bit. I'm just giving you the overview of them, including the Armstrong. I just want you to know what is the basic understanding, and you will have to spend some time, try to print out the variables, try to run it with different examples, and try to make sure you understand them. Okay. So that is most of the simple examples, right? Next, I think I should, okay. We'll go into this number conversion example. And then after that, we'll just briefly discuss the exercises. Exercise 1, actually, because some of the parts of exercise 1, we are doing it here. Actually. And then we will go into, finally, in the next hour, we'll go back to the cashier program. Okay. So let's just go into, since we are dealing with numbers. And yesterday I said that Pingala is one of the ancient scientists whose name has been covered in history with this decimal number system. So that's why I renamed this program to promote his name. Okay, so just running that number system. So what is this lesson about? This lesson is about actually converting a decimal number into binary and a binary number to decimal, right? So some of you who are all new to, some of you are really new to programming, and some of you are more intermediate users and know about this. But those of you who are really new to programming, I briefly discussed yesterday. And okay, let's say it says control click. Okay, follow the link. So as I discussed yesterday briefly, that everything that you type on the computer is converted into a decimal number and then finally converted into a binary, right? So for example, null escape character, that's the decimal number is 27. Space, the space that the decimal number is 32, and its binary is this. And asterisk, the decimal number is 42, and that's the binary. And then you have your uppercase and lowercase and everything else afterwards. I didn't know there were all these other signs, but yes, some of this is the extended ASCII code. So our lesson today is about how is a decimal number converted into its binary, and then how a binary can be converted into decimal. Okay. So, and once you've mastered this, you can also do the conversion of binary to hexadecimal, binary to octadecimal, decimal to octadecimal, decimal to hexadecimal in any ways. Okay. So, and that will be a minor exercise that I will add to the exercise 2. Okay. I will define an exercise about this. So how do we go about doing this? So we can see just from this table that 4 is, if we just don't consider all the digits before it, in 4 is represented as 100. So 100 in binary is number 4. 101 in binary is number 5 in decimal, and 111 in binary is number 7 in decimal, and 4 ones in binary is number 15 in decimal, and 5 ones in binary is number 31 in decimal, right? And all zeros in binary is 0 in decimal. Okay, so I think you all get the point by now. So basically, we first do the decimal to binary conversion. So let's say the number that we ask the user is 9, and we call this decimal underscore binary function, and that function is implemented here, and that function is using recursion because it's just calling itself. Okay. So how does it work? So the 9 here, it says you take the number 9 basically, and if that number is greater than equal to 1, then you call that number again, but in the calling function you give it number is equal to number divided by 2. Okay, so let's just print the number here. To see what it does. So you can see it does show these numbers there. For some reason. So okay, let's do this ourselves. So 9, how would it be in decimal? So basically you divide the number by 2. So you divide it by 2. Then what is the division? If you take, let's say, the integer value of that number. So the number is what is 9 divided by 2? Int of that. Anybody? 4, right? Great. So the first time around, it just got that number 4, right? And then what it prints, it gets the number, right? And in this same function, basically it prints the modulus. So what is the modulus? Anybody? 9 modulus 2. 1. Great. Thanks, Johannes. Great. So that's the modulus. So that's the first thing you got. Then, because the function now calls itself, and the next round it gets the number 4. So what will we do? We'll do a 4 divided by 2. And what is that? And 4 modulus 2. What is that? The first one, anybody? 4 divided by 2, the integer of that. and 4 modulus 2. 4 divided by 2 is 2. Thanks, Ansh. And 4 modulus 2 is, what is 4 modulus 2? Okay, 0, right? So, okay, so we got that. And now we will do our new number now is 2. And then you'll do 2 divided by 2. What is 2 divided by 2? And what is the modulus? 2 modulus 2. Anybody? Thanks, Ayu and Tiani. So that's 1 and 0. And now the last one, because the rule here is if the number is greater than or equal to, and 1 is equal to 1. So that means 1 modulus 2. And what will be this combination? Anybody? What would be this? Note that this automatically because makes it an integer. Okay, 1 divided by 2. Thanks. And 1 modulus 2 is 1. Basically, the smaller number is the modulus. So basically, what is happening now, because this is not going to work here, so basically the loop ends there, right? So what we have, all the modulus signs, if we collect from the top, all the modulus signs, we have 1, 0, 1, 0, 0, 1. Okay, and that is basically the binary number, basically. Okay, so this becomes a bit confusing because there's a print statement here, and then the modulus print statement is there. So that's the reason it's better to not put this print statement there, right? So this is basically 9 is in here. It's, we run this, and basically that's how it works, right? So saying 0, 1, 0, 0, 1, that's basically 9. So that's a way to use recursion to do that. The formula remains the same, basically. And you can also use the repetition to do this. And with repetition, we have another implementation with a while loop. Note that this implementation is not very good in the sense that there's no return value, right? It's not returning anything, so it's just printing it out there. So we cannot use that value in other functions, right? So when you are using functions, it's good to have return value so that you can give some task to some function. That function does the task and returns you something, and the return value you give it to another function, right? Something like that. So here in the binary case, the iteration case, we have a return. Okay, so here basically the formula remains the same, but what is happening is as we are going, we are kind of appending that to a list, whatever we are getting, right? So that's appending to a list, and then we basically, in this case, we are then returning the list later, and somehow it's converting it into a string, I guess. Let's see. Okay, what we get. So for the number, the same number, we got the binary value, and because whatever it returned, but note that what it returned was in a form of a string, right? So I mean, if we want to kind of place whatever we got, because now the next program that we have, the next function, it takes into that same binary, and it should be able to convert that back. So whatever we got it as a string, and that was basically 1001, and then we now need to convert it into a decimal value, and because we got it as a string, we converted it into int, and we pass it to this function called binary decimal. And the way you convert it, let's say conversion is more simple. You have 1001, which is same as saying 1 multiplied by 2 to the power of, so you look at the power, which is so it's this multiplied by 2 to the power of number of the place value, basically. Okay, so it's this multiplied by 2, the place value minus 1. So it's how many values are there? 1, 2, 3, 4 to the power of, so it's 4 minus 1 essentially, right? Plus, right, 0 multiplied by 2 to the power 2 plus 0 multiplied by 2 to the power of 1 plus 1 multiplied by 2 to the power of 0, right? That makes sense. So that will give the conversion. So that's what essentially is done here. So how would you take each of these values out? This value 0, 1, 0, 1. That is, remember how we did it in the Armstrong number, right? So that similar pattern is there. So it's very important to master the Armstrong number, how this binary, decimal, and decimal to binary conversion is done. So binary is basically base 2. Base 2 means that the numbers that you are going to be will be 0 or 1. So whereas octadecimal, so octadecimal numbers that means it's base 8, and hexadecimal numbers base 16. So that means in octadecimal we'll have 0, 1, 2, 3, 4, 5, 6, 7. So that means a number, let's say if there's a number is 50, what is its octadecimal value? If there's number 50, what's hexadecimal value? If the number is 50, what is binary value? That's what I was trying to imply. So if, for example, the number 50, that's the binary, right? And that's the octadecimal, and this is the hexadecimal, right? The thing is, in hexadecimal, because the base is 16, so it's like going from 1 to 15, right? But you don't want to use 2 digits to represent a number. So what happens is you see 2i. So in the place of 10, you use I. In the place of 11, you use B, and so on. So that's why in the hexadecimal, you'll always see a number and a letter. So that's the difference between octadecimal and hexadecimal. You can read about these two, and this will be part of your exercise 2 or 3, something like that. I have to decide. We'll just probably make it a part of exercise 3. So okay, so we are almost nearing the first hour, end of the first hour. So this is how it's done, right? And this is how it's implemented. Basically, you do take the decimal value and so on. Let's just print this to see what's going on. Okay. Okay, I just put a plus to know that we are there. So you can see the thing is that that binary number that was supplied to it, first the number 9 was supplied to it. It was 01001, and then later the number, this number was supplied to it. So what it did in the case of this, see at the end is like triple ones, right? So 1000111. So it took the last digit out and it printed whatever is the remaining. Then it takes the last digit out, then it printed whatever is the remaining, printed, and so on and so on. And that same thing is 1001. The last digit is taken out and it's printing whatever is the remaining, because it's using modulus. And then basically whatever is the last digit that was taken out, that is multiplied by 2 to the power of I, actually. And the I is basically starting from 0. Okay, so basically it starts from here. Actually, it goes it starts from here. So it takes the, I think the first one, because the first one is like is a palindromin, meaning that the number that you read from front and the back is the same, right? So that's palindromin. So it's not a good example to do this. I think the second example is good. So I was saying yesterday about the movie Tenet. That Tenet, the beauty of Tenet is that's also a palindromin. So the way you read from the back and the front, it's the same. So there are a number of examples of palindromin, and function to determine if a number is palindromin we'll discuss in the coming lessons, and not today. So that's so here we have 1 0, these ones, right? So it starts from the back basically, and then it keeps on building. So the first thing is that one is in decimal is 1. Then it's 1 plus this one place value, right? And that's 1 plus the 1 is added, and then it comes to this value, then it's added to, it becomes 7. And then see the thing is here, if the number is 1, then the binary is 1, right? If the number is 10, then the binary is 2. If the number is, then the binary is 4. And if the number is 1, then the binary is 4. What is the binary? What do you think is the binary? So in this way, basically, it's starting from this end, and it keeps accumulating, and then it keeps on accumulating, and then Why do we have these repetitive sevens here? Why? Because there's these two guys here, they had zeros, and we know in our formula 0 times 2 to the power something or 0 times 2 to the power any other number will be 0. So that's why nothing is added to the 7. Okay, and then finally when it processes this, then that 7 becomes 39. Basically number, because this number is 32. Okay, so that's how 32 plus 7 is 39, and this represents the number 3. So this is all about binary to decimal and decimal to binary. And when you are going to change the base, basically it will be, let's say you want to do with octadecimal, it will be instead of 2, the base will be another number. So octadecimal, the base is 8. So that's something to study, and that could be part of the exercise. Okay, we'll move on to the next one, which is numerical integration. Okay, well, before we go into this one, I want to kind of go back to our exercises. Right. And yes, if you join later, I just said I'm a bit disappointed that nobody is giving me solutions, or people are not using the forum to share solutions or part of the solutions or create a discussion. This bootcamp shouldn't be just one way from my side to yours. It should be both ways. And I would like to see more and more discussions in the forums, people sharing some code, people sharing code which is not working and asking others for help, that, hey, I have an error, can somebody see this error? Just like it's done in Stack Overflow. You can use Dropbox to share your code, you can use GitHub to share your code, and so on. We are a team here, okay? So let's do this together. So this the body mass index one, I think we've done so many exercises now. By now, this whole thing would be quite easy for you to do, right? Because we did a speed find calculator, and basically you're supposed to take that same program and just edit that program, the format of that for the speed find calculator, and you can do this. And all this information that you are asking from the user, these things are fine. But this last part, your program should run and calculate BMI as many times as the user would like, and the program should exit when the user explicitly specifies. So that would be like, so the first message in the program should be, would you like to calculate a BMI? Then you say enter. So there should be a while statement. So that your whole main, the functions that are the BMI function that is called in your main function, that should be inside the while statement. So, and it keeps on being called, right? So hopefully towards the end, or sometimes some people can give me the solution, their solutions, then I can discuss that. Or towards the end, if nobody gives it, then I will basically go over it myself. So that's the BMI. And the second one was the code correction, and essentially it's supposed to improve this poor coding skill here. So the way you should go about it is instead of having this array, a series of one-dimensional array, this whole thing can be just, so how many are there? 1, 2, 3, 4, 12, 13. So it should be just zeros, but 2 dimensions. So that means 20 by 13, 20 by 13, basically. And that one line would replace all of these. And that this is basically initializing it to zeros, like all of your arrays. but this is not needed because your arrays are already, your 2D array will already be initialized to zeros. And even this one is already initialized to zero. So this basically code does not really help. It doesn't do anything. So that is again another poor programming. And in this one, you could, because it's a array, now 2D array, all this goes out and you just print, you can just save the whole 2D array, right? And note that the format here basically means how many decimal places. I mean, this for now, the 2 decimal places is okay, but here in the exercise, I do ask other things here, which is try to make this program, you know, you can use random number generation to fill the values of the matrix and then do some things to the matrix operations and plot heat maps and histograms. Seriously, this is not very hard. Okay, so please try to attempt this. And all these others, like we already discussed, similar examples, and you have to play with them. This one you have to think a bit. And if somebody can do it, do share your ideas. And sometimes, like in the forum, you can, if you haven't done it, if you have an algorithm that does it, just share the algorithm and ask people, is this the right way to do it? So moving to part 3, which was loops, the prime part is done. We already did the prime function, and you have to just put it together, and that returns that. So I think yeah, and you just have to try part 4 by the fundamental theorem of arithmetic. So what this does, so whatever function we did with the prime, use that and try part 4, whatever we did on the prime just now in today's class. Then this one is about a maze. Oh, sorry, it's about computation, right? So you have a function and you want to integrate that function, right? That's what this is about. So I will just go over a very basic example on how this can be done. What do we mean by a function? How should we do this? And then finally, okay, let me just open this new tab and go on to the 5. And part 5 is actually a maze navigation program, and I was just trying to put the algorithm down so that you can implement this. And yeah, so that's the maze navigation assignment. Okay, so we'll just take a 2-3 minutes break now, and then after having some water, tea, go refresh yourself for a few minutes, and then we'll return in 2 to 3 minutes. Okay, and go over the rest of the lesson. Okay, let's continue. Kind of have approximately 50 minutes now. Uh, where is what? Okay, so there we are. Feel free to put any comments, any questions on the chat. So I have a separate computer where I can see the chat. Right. So we did talk about a bit of this numerical integration. So let's see what this is about. So so this is just to give you more hints to do that exercise. It looks complex, but that exercise is not as complex as you would think. So I just got this from this page. Let's say that this is our function. So numerical integration is for any function that can be defined here, something like this. Like, so we have x to the power 4 multiplied by 1x to the power of 4 divided by 1 plus x squared. Okay, so quite a nice function there. I wonder what it looks like when it's plotted. Surely it won't be looking anything like this, but there is this function as well. Some function is here, right? So it can be any function like that, or it could be just x squared, you know, something like that, just x squared or x cubed, right? We know how the x cubed function looks like. We know how x squared function looks like. So integration is basically you want to find the area underneath the line, right? That's what integration is. And in here, basically this is the function. In integration is we want to find what is the area, and basically we want to find it between some range. The range here is -2 to 2. So I and B is 2 to 2, you know, something like that. So integration can be computed, can be done theoretically, or when the function is very complex, then you need to do is do integration this way, numerically. So numerical integration is this is the basic form where you kind of, you know, divide that function into pieces. So basically you iterate over that function. So your x basically is between -2 to 2. So let's say that you use a line space x or something like where you iterate, you have some kind of a step size, and your step size is 0.5. In this case, the step size seems to be 0.25 actually. So because you can see between -2 and -1, the function has been divided into 4 pieces. So here the step size is 0.25. So basically you put -2 in that function, and then you will get a y value, right? Then you'll do a -1.75. Then you'll get another y value. Then you'll do a 1.5, here is minus 1.5, you will get another y value. Basically, the y value is your height. You can think of the y value as your height, and basically you are making these rectangles because you know your height. If you know your height, let's say you know the height, and if you know what is the width, then the width multiplied by the height gives the area of the rectangle. And this function is basically can be approximated by adding all the areas of all of these rectangles, basically. And that's basically the numerical integration. Okay, so that's the numerical integration part. And here it is implemented in this way, where you have so the way is either you use a rectangle or you could use a trapezium. So a trapezium is basically like you have a rectangle where one side is smaller than the other, and then you have like a triangle at the top. That's what a trapezium is, and that's what a trapezium looks like. Okay, so this is a trapezium. So you can see the error between the trapeziums and the function is basically a little, this is much better than the previous one. And you can see that this was I plus b divided by 2, right? So that's whatever is the I value plus the b value divided by 2 multiplied by the b minus I, that was giving the, you know, and you do it in small parts, that would be giving the area. Whereas in this one is, it's I plus b divided by 2 and then multiply. So that's the difference between the two versions. So the one that is here in this example, that's the trapezium version, I guess. So as it says so. And note that here basically that function, trapezium function is called, and you could pass it the func name basically. If you don't pass anything, still this will be working. Okay. Here, because the function is just right in this same file, so it will just taking the function, the value 0 value, the value 1, and this is basically integrating it in between 0 and 1. So at the moment, this function is not taking two different values for I and B, right? So it is basically going, it is not, it is assuming it's between I and B, but it takes the number of steps. Whereas what I was talking about is step size. So either you give it a step size or you take it, give it as number of steps. And in here, the number of steps is given. And basically for that function, we are iterating over all those steps. And which is given, which is 100 in this case. And we are multiplying and basically adding the, so this to the sum basically, right? So we keep on updating the sum, and basically that's how the numerical integration is performed. So I would like you to kind of read more about this and try this and try to do that exercise. So this is more of the hint. Okay, so moving on, we have another example. And basically that example is, this kind of gives hint to the maze navigation, right? So when we think about the maze problem, that's the final part of exercise 1. When we think about the maze, what is happening is, this is the first example where we are thinking in terms of, we are thinking spatially, you know, we have a map basically. And when we are thinking spatially, we need to use graph representation, right? And a graph can be represented as a list, agency list, or an agency matrix, right? So what we mean by a graph is we will discuss a graph in Thursday and Friday as well. So we'll go into more details. But for here, just note that if you want to have a spatial system kind of represented in computer memory, then you should use implement it using a matrix, basically, right? So what is that figure there, and what is this? Is that in this example, basically we want a robot to move from the source and go to the destination, and this shaded parts are walls, and these white parts are the space you can move around, right? It's very simple. I mean, in most offices we have walls, most houses, there are walls, and there's spaces we can move about, there are corridors, and basically we want to avoid the walls. We shouldn't be hitting on the walls, right? So to go to the destination, and basically the destination can be from one room to another in a real life situation, okay? And let's say that a robot needs to be done, because a robot generally, we think that the robot is intelligent, but an unprogrammed robot is the most unintelligent person. It's basically a stupid person, right? But if we program it, then it becomes more and more intelligent, depending on the programming. So this is using recursion and the idea of backtracking, and basically to navigate through a space, right? So that's the 2D space. So this is the map, basically, and here we have that. Basically all the zeros here basically means that they are the walls, and the ones are the things, they are empty spaces where you can move around, right? So essentially, basically, if you want to know, I mean, for example, in this maze world, so this is a world of its own, let's say. So your 0 and 0, that is actually, what would that be? That's your 1. So that means yes, you can go there, right? You can go to 0, 1, but you can't go to, so sorry, yes, 0, 1s are you places where you can go, but you can't go to 0 and 1, which is this. You can't, this is a wall, basically, you can't be there, right? So that's a major limitation. So basically you need to avoid the wall. So all the places basically where you find zeros, don't go there, right? That's the basic thing. So there's a solve maze function here, and basically this function can be used to do your exercise part 5. Okay, so solve maze function basically is quite simple, and we have a function which is called solve maze, and that function is called from here, right? So it basically takes the maze, and it creates a, because we are not using numpy arrays here, right? So to create a matrix which has all zeros, basically, that is a solution matrix. This is so that after we have done this, we get this another matrix, a solution matrix, which shows how the robot moved, right? So we create a same size matrix, but it's just initialized with zeros. And then we have, we call the maze, solve maze utility function. And when we call that function, basically, if it returns a false, basically you say that there's no solution. That means you can't go from one end to the other. The goal is to go from one end to the other. If you are kind of trapped in the middle, then the function will not return. Then the function would return a false. Okay. Or and then otherwise, if the solution exists, that you just print this, print and then you just retain a tree. Okay, so we go into the solve maze utility. So what it is taking? It is taking the maze, which is your map. Basically, it's taking a x and a y. That means the initial position. So that's 0 and 0. Okay, so in here, in this case, it's taking this position, that's source, right? And it's taking this whole map, but it is not taking this path. It is its job is to find this path. Okay. So we go back, and basically, if your x, it is in the Python world, basically, if you have a global variable which is constant, which will not be changed, you should generally initialize it to, n of to capital numbers, basically. So here n is 4. That means our maze is 4 by 4. In the robot example, you can have like a 10 by 10 maze, right? And you can basically make that 10 by 10 yourself. You give something like this, and you let the robot move around. Basically, you can have walls and paths, and in one of them, you can just say -1. -1 in that one maze navigation, you can say if -1, that means the robot has found something important. It's found the source or gold or price, something like that. In that, so that one can be changed that way. But here we have, so it says if it is the goal, that means the goal in this one is that either your x or the y, you have reached a wall, and the wall is n-1. If your x is either x, or if you're both x and y are basically 3 and 3. So what is the goal here? So your x and y is 3. So which is here. This is your goal. So if you get this, basically that means your maze is solved. Okay. So that's the goal. So in different types of maze navigation, you can set your goals differently. Like, let's say if you wanted your goal to be here, then you will just say that is the coordinates will be different for the goal. This will be n-2. So or n-3, something like that. Yeah, I think that would be n-3 if the goal is here. And if the goal is here, what would it be? Any one wants to tell what the goal would be? What would be the value of x and y if this was the goal? Anybody wants to say it in the chat? What would be your x and y if the goal was here? So what is this x? That's your row. What's the row? And what is the column if this is the goal? Anybody? Okay, so thank you, Jordan. So yes, x is 2 and then the y is 1. Okay, so that means this will be the goal. So if we wanted to change the program a bit, we can change this part. Okay, so that's your base case. Otherwise, you basically move forward in x direction or you move forward in the y direction. Forward in the x direction, meaning you go down, or you go this way. So there's no things like you return back, there's this robot can only move front or sideways, something like that. Front or sideways. This is the robot. If you want the robot to move back and sideways, then you would have to add more if statements in this robot. At the moment, this robot can move only front and sideways. So that's adding more statements there basically means you are addressing your exercise 1 part 5. Okay, so what happens is basically if then you call, basically here this means you are calling the function. You are calling the function, and while calling the function, the same function again, that's a recursion, you are passing it the same maze, but instead of x, you are saying x plus 1 because it's moving forward in the x direction. Because if the robot was here, it would move here. If robot is here, it would move here. So this, the robot comes here, this will be true. Okay, so this would be saying true, forward in the x direction. So let's just see what's the first thing. So we just printed that and we're just saying, okay, where's the base case? So that's the base case. And the first thing is the first time around, it's saying the base case. I don't get why. The first time around should be 0 and 0. Okay. So probably this will come later. So the first time is what you are giving to your robot. You should be giving so yeah, so this is the first operation that happens actually. Forward in the x direction. So you have a 1 and a 0, right? And then move down in y direction. That's this one, move down in y direction. So your robot here depends where you are. So and then it says move forward in the x direction. And then move forward in the x direction. So it depends how its x and y is. And in here, the forward in the x direction, it seems it means this, and move down in the y direction. Sorry, my naming may be a bit wrong, but generally this is what's happening actually. And then eventually you get to the base case. So this is an example how a very simple spatial setup of a robot. And as you see, the next one is actually, which is move down in the y direction. That's where the y, it's y plus 1. Okay. So and then in the y plus 1, you are basically calling this function again. Then that function comes and then it will either do this and that. Then you'll call it again, it will either do this and that. But every time you call again, it will first check this. So a time will come when your both x and the y will become 3. Both of them will become 3. And then basically this base case comes and then the recursors back. Then it will recurse back. So what happens, the reason you see the base case coming first is because first it's not actually it will go just like your Fibonacci and factorial. It will start calling all these functions and then it will only start printing when it recurses back basically. So this is try to study this a bit and then we'll go over it again later next week, where we'll try to attempt that path problem with for the robot navigation, where we have more things in here and then we should have a better way. At the moment it's a bit confusing, I understand why, because we are not really printing the maze as the robot is moving. So that's what we need to do. Basically these things are not really very useful. What would be useful is that the whole maze is being printed as the robot is moving. Okay, so that means the solution is being printed as the robot is moving. And note that there's also we need to all these, both of these ifs are happening only when the maze is valid. That means the is safe is being called here. Okay, So the first thing is, before it's calling both of these, it goes in here, checks this doesn't happen, then it will check this and it will call itself, right? So that's another part. And once it calls itself, then it will start basically calling the others. So next week we'll try to make a good diagram of this and understand this. Okay, so now we are going to move into more planning for your exercise 2, and that happens once we do Acacia program. And yesterday we did try to we know that we have a vending machine project. Okay, so before we study that project, we just try to say more of exercise. We call it exercise, but these are kind of small projects. Right, so remember yesterday's GIF change? What I did was I took that GIF change and then I called that Acacia basically. So let's go back to yesterday's class, and then this is the Acacia function yesterday, right? And we basically did some operations there and trying to understand how it works. Now we're going to, so we took that. And so we just asked, let's simulate a Acacia machine. Okay, we asked the user, let's simulate a Acacia machine. And we know that the Acacia machine that is there, we have a number of stacks of coins. And in each of those stacks, let's say that we assume that we have these globals and we have 5 coins each. And we have the different denominations. So these are the coin denominations: 50 cents, 20 cents, 10 cents, 5 cents, let's say. And this basically tells how many coins to give. Okay. And what we want is that the coins stack to increase the number of coins at some point when we get more money. But at the moment, let's just run this. So let's simulate Acacia machine. Assume that you selected items with the following cost. I'm just putting this cost, So let's assume that this person went to a store and for 75 cents. Let's assume that this is in the era of the 90s. Okay, so you have things which are very cheap. This for 75 cents, you won't get anything. Okay, but in the 90s, when we used to go to stores as kids, things were more affordable. If we have 75 cents, that was a big deal. Now that 75 cents may be worth maybe similar to $5 or something like that. So okay, pay the cost. So that's what it's saying. It's telling the user pay this 75 cents, right? And let's say the user had a $2 note, right? So it says your change is 125, and that's what's computed by this function change. So before that function change is done, oh yeah, before that's what the change is, but before that, it's asking get money, right? So that's what this place where it asks you to input. So that's what we got the money, and then the amount that was input, which is 200 minus the cost. This function takes the cost, which is 75, and it just returns the difference, right? Change. So whatever the change is, basically, it takes that change and checks if that is greater than 0. Right? If it is greater than 0, then it calls the give change function. Otherwise, it says you do not have, you have not given enough. So that is like if we run the program and we give 45 cents, it's because your change is minus 30, 45 minus 75, and you have not given enough. So then the cashier basically tells you, and you're supposed to give more money. So let's do this again for 200, right? So, and basically you get a, says for 100, for your change of $1.25, you give 250 cents, 120 cents, and 15 cents, right? So that is the change of that give change function. And again, we are coming across this the beauty beauty of using division and modulus, that kind of thing, which is used in the Armstrong or the binary number and the repetition. So that can be implemented either using a while loop, or you could always use a for loop to do that. At the moment, to give the change, we are basically playing with this int change divided by the coins. We take it. So basically we are doing 125 divided by what was the denomination at where we are at. But yesterday, remember that I was like trying to play with this and say, hey, can we check that we have enough of this, right? So if you have number of coins where the number of coins of 50 cents is 0, because we did not have this check yesterday. So now we are checking if the number of coins is greater than 0, then we will give that change coin. Okay. So that's how it's implemented. So let's say that we run this program again, and in this time, the number of, we still do that. So because the number of coins are 0 here, basically you're not giving any 50 cents. It's saying 0 times, but then you move into your next one, you're giving 20 cents. But then the 20 cent is given 6 times, right? So the problem here then comes is like, why is this -1? It shouldn't be -1, because so in this style, basically what happens is you have a problem naturally, because the next one, if you don't have enough of the next one, but it kind of gives it as a loan. But for now, we just leave with this. We don't want to, we want to iteratively build a solution. Okay, we don't want to say, okay, this is not working, so now everything is not working. Okay, we want to iterate. We don't, in programming world, there's not a 0 or a 1. There are things in between. At the moment, something is working, and we are going to use this in the future, and we are going to brainstorm how this issue is going to be solved. We know that the first issue was there, it's kind of solved. We don't give 50 cents when we don't have 50 cents. Okay, so essentially then the coins are given, right? And the give change basically gives these coins. So that basically ends the cashier simulation. What needs to be done actually, when the change is given out, whatever the amount is given by the person, because the price, the cost is 75 cents. The person gave you a $2 note, and basically let's assume that the $2 was given as 250 cents and 520 cents, right? Okay, no, sorry, I'm making a mistake. So let's leave the $2 as $2, because if it was given as 250 cents and 520 cents, then that person wouldn't need to be given a change. The cashier doesn't need to process it any further. So we leave that as it is. The point I'm trying to make is that whatever the person gives to the cashier, that should be eventually updated in this coins stack. Okay. And basically, if it's a $2 note, like we can always put a $2 and $1 notes here, right? And let's say that these are the values. So whatever that, so the $2 note that was given, the number of, okay, let's just assume, let's take this note thing out. Okay, let's say that there's a $2 coin. Let's assume that all are coins, right? So number of coins, this should be updated from 5 to 6. Okay. So it is saying, of course, it can't give this, but now because we have a $1 note, and so it gave that out, $1, it didn't give a 50 cents, so it gave $1, it gave a 20 cent, it gave a 5 cents. Okay. So that is all good, and that's the number of coins we have left. But you can see there, this was 5, and we have 5 there, and the $1 was given, so that 1 is now a 0, and your the last 5, I mean that 20 cent was given out, that's a 4, that's a 4. Okay, so far it's working out well to some level. Okay, so but what we want is the 5 that was there, because the user gave the $2 coins, and let's say that we always assume that the person just gives these coin denominations, so that $2 is basically should be updated, right? So your the number of coins at the moment when we give out the number of coins, basically we are decreasing the number of coins somewhere, right? But then because the whatever the give coins is, that is being decreased, right? But now we need a way to, when that money comes in, when this since the transaction is successful, that means the person has got the $2, the $2 here basically needs to increase from 5 to 6. Okay, so that's something for you to think about. Okay, how will you do that? And leaving that note, I now move into the project session 2, which is the vending machine. As we are going, slowly moving, the more and more you do these exercises, the more and more you will realize that you are becoming better at programming. So the vending machine is basically, yeah, this is just a previous assignments I gave to my classes in Fiji and other places, and we were, so it's a big workload, 15 hours, because this is a boot camp. Then it's supposed to be like you work today and tomorrow and the following day, and you spend this much of time, assuming that you don't do anything else. But since all of you are doing other things, a lot of you are doing other things, then you can do this later as well. So this is what is on the offer in the vending machine. We need to create a vending machine class and implement method. Show menu, make selection, return change, and display a message with the appropriate parameters. Appropriate data encapsulation techniques should be used. Okay, so you should have these 4 functions. Your program should be written in such a way that it can easily be changed to accommodate new items. For sale and different point denominations, changes to your program should be limited to the declaration part. If the current balance is not sufficient to cover customer selection, then the vending machine will prompt the user to deposit more money. delivering the selected item, the customer has to keep topping up the amount until the balance is sufficient to cover the price in selected item. So all these exercises we have been doing, now you are being tested. You are being tested, you are being challenged to start thinking how all these exercises, how these technologies are going to be used to develop this. As part of the routine maintenance, when the selection 99 is entered, the vending machine will expect a secret PIN code in order for maintenance to proceed. Do not display this selection to the customer. All items in the vending machine are restocked. Also, the number of sales for each item, the total balance given, in the net income for that day are displayed. Okay, so this is a bit more interesting. And if you have done these three, then doing this won't be that hard. Assume that the vending machine starts every morning with a fixed number of coins of each denomination. If the vending machine has run out of a particular coin, then alternate means for giving change must be found. If no accurate change can be returned to the customer, then his or her current selection will be ignored. Okay, so this is what we have been trying to implement. And your machine should monitor if you have enough items. If you do not have enough items, your machine should print a message that can be emailed or placed in a file, and is the greeting. It's a good exercise to test all these different things. And basically, because this was first given in C++, then this is what I gave to my students back in the days as a skeleton code, right? So the skeleton code, and this can be very easily converted to Python, but I'll just discuss the skeleton code. And note that in C++, it's not so easy like Python, where with one print statement, the whole list gets printed out. So you will have to always write a for loop to print things out. And the curly braces, that's the way that things are done in C++. So these things, basically coins, number of coins, we already have in our vending machine. So you can just use the same thing. Let's do this. Okay, so let me save this as because we can keep on discussing this as something in session 4. And in session 4 we have we'll have session 4 on Thursday, and by then you should have attempted this, and at least the first 3 parts, been successful in doing this. So I'll just create this there, and I'll call this VM. This is I copy and self-plagiarize. And self-plagiarism or plagiarism of other people's code in the programming world is quite okay, as long as you can cite them and give credit to people. So okay, so these things are there, right? So let's just assume for simplicity we place the price and things all on top. Okay, so let's say this is item price, so we place these things there. See, and then there's the number of items. So just curly to square, and this makes it Pythony. Or better word, snaky. So from C to Python, and then we have a number of items. Okay, so just like you have been monitoring your coins, you need to monitor your items. So these are your items. Well, basically it means things that you have there, like your these things, This assignment was also given in Turkey when I was there in Northern Cyprus with Professor Krishna. That's why we have Turkish delight. We can change this to something Australian, I guess. So at the moment we are not telling what those items are, but you can have item name as you know, a list as well, that we can deal with this part later, you know. So for example, Coke and the rest of it, and so on. Don't have time to say now. Right, so that's the item name, and basically you will have all these functions, and we'll complete all this on Thursday, but you can continue with this. And you see that these functions, we have print confidential information. Basically that's just printing everything what your machine has. Okay, so because these things are now global, meaning we don't have to pass that. So we have def so this function it will just print the state of all these things. So for example, number of coins, and for example, we're just saying the two of them, right? And so that's the print confidential information. And similar to that, we'll have a menu. We need to have a function called show menu, basically. And in show menu, what you're supposed to do is basically print item names. And print your item. So you assume that a customer can see how many items are there and what are the things, what are the names, and you can print them. I mean, this may not be the right way to print, but the item price as well. So they know that there's that many items there. That's the name of the item and that's the price. And this is a terrible way of printing. You can print it in a nicer way where it shows the item name, then it gives its price, and it lists how many number of items are there. You know? So that's the first and then we have give change, but then we have a major function here, which is make selection. Okay, make selection. And the make selection is an interesting one because the make selection function is supposed to use your show menu and it's going to basically give the user all this information. So you're supposed to call your show menu that, and then that's where it's being used. And then it's supposed to ask the user to enter items, right? So this is the part we are about to finish in the next few minutes. Sorry, I have to take a little bit more time. So let's say that the items that are listed, I mean, these things are going to be shown in the show menu, right? So if the user wants to, let's say, have 2 Coke and 2, then you are just going to show it the item ID and tell the user that you enter. So if the user enters something like this, 1 1 2 3, something like this means that 2 of the first item and what needs to be happening. So this is what the user enters, and you should take this and convert it into, you should take this and then separate it as 1, 1, 2, 3, right? And this you are going to use some kind of a for or while loop using you know using mod and division to basically separate these things, and then you take each of them, right? And you let, so you separate them, and then you basically refer to item list and price. Basically, if you have something like, let's say you want to now calculate the sum, right? So sum is 0, right? And after the user basically makes the selection, if the item is there, then you return the sum. What is the sum? Is what's the total of the selected items by the user, right? So you ask the user for these things and use these things to get add to the sum. So your sum, for example, sum is equal to, right, item price, whatever you got, right? So you will always do it, you get some index -1. So this is like your index that you get. Why it is -1? Because we know that our list starts from 0. So when the user enters 2 ones, it will be the first thing in the item, which is Coke, which is 75 cents. But we will refer to calculate the price, item price. Okay, so this whole thing should be done in some kind of a while loop or a for loop, where you should get the item price. If you can do this, then that will be great. So you get the price. Then once this price is working, then you should also put a if statement in your while loop. You should only calculate the item if this number of items is greater than 0. Okay, if the number of items is greater than 0, then you should add it into the sum. That means you have those items. Okay, so that's your show menu. Show menu is using these things. Make selection is calculating this. And then once you have given, once the user, then you ask the user to give the money, some of these ideas will be reused. And if the user gives the money, then after that you should calculate the change, then give the change, the coin things comes there. Then you should have a function or a way to ensure that the number of items basically decreases, because you've given 2 Coke, now your Coke should be 8. You've given the coins, these coins should decrease, things like that. Okay, so let me just quickly compile this and push it, and we're nearing the end. So now I leave the floor open to comments and questions. For comments and questions. Can you do it? Can you try? Anybody? Please say yes if you are going to give it a try. And by Thursday, you'll have something. Nobody is confident. Nobody wants to try. That's so sad. So yeah, actually, this is at least working for now. I'll just push this. Nobody wants to try? Oh, great. Thank you so much, Jody. You have motivated me to carry on the boot camp, or else I would be like sending an email soon to everybody that, sorry, it seems nobody is trying any of the exercises. I'm the only guy here, and let me just end this boot camp. Okay, so if people don't try, people don't participate, I'll have no option but to just end the boot camp. Okay. Okay, so I'm pushing all this, and I'll just do a stop share and stop recording. Please put your comments or say anything you like.